Okay, so welcome to the first class in StatMech, where we shall discuss how the course is going to go on, what is the plan of the course, why study StatMech, what is the history of StatMech, and how it is connected to thermodynamics. And having explained a bit of that, I hope in the beginning of the next class to start with how and why StatMech is used in today's times. It's used in a very wide variety of ways. So I can just tell you about some things that I know. Its uses are beyond what one person can summarize in 5 minutes. But at least some idea you will get why you should be investing the next 4 months to learn about StatMech 1. Its main uses you shall learn more in the coming courses. Uh, and then we will have a brief overview of thermodynamics, maybe 2 or 3 days, and some of those ideas we will be using while calculating quantities of StatMech. Okay, but before it, when we get into the physics, so let's me tell you that this course, the way it will be evaluated, it will have a first quiz, which will be in the 5th week around 7th Feb, say, and it will have 25% of the marks. The reason it will have such high percentage for quiz is the first 1 month that you shall be studying. That's really the foundations of it, and what you'll be seeing after that will be application. So those foundations are extremely important, and if you don't focus on those, the rest of the course will go haywire. The midsem will be at the end of 2 months, and so that will have 30% of the marks. So where again a lot of the first month's topics will be covered. There'll be no second quiz, and the finals will have 45%. So basically 25 plus 30 is 55%. The finals will have 45%, and it will cover the entire syllabus. So the pattern of questions will be basically what is covered in class, and there'll be a large number of questions. The idea is every small bit, are you getting a strong handle on it or not? There won't be too many tough questions. The StatMech getting used to the concepts is uh, a bit intricate, as you will see. So even standard questions, if you handle all the different topics in a good way, that is the aim of StatMech 1, so that one can build on it. These simple concepts one can build on it in their future courses. Now, there are some of you who well, for whatever reason, if one has to give extra remedial exams after the final, so they get an extra advantage. They get to know what is the final exam marks, sorry, question paper, and also which questions came in the final exams. They have this, like they get extra time to prepare. So these remedial or whatever they are called, the exam which one has after the final exams are over, in case there's somebody got F or somebody who misses various the final exam, so that is going to be really tough, because it's going to base uh, that's going to be based on to nullify the extra advantages that the students are going. So there will be some basically application of StatMech principles from research papers, where I should give steps, but you have to work very hard to get if you're appearing for an an exam beyond the finals. Uh, so statistical physics or statistical mechanics essentially consists of the physics of large number of interacting particles at a finite temperature. So there is this concept of heat and energy exchange from a reservoir and an interacting system. Typically, we are looking at the properties of a system, say a room of gas or a box of gas. And depending upon different conditions, adiabatic conditions or whatever, closed, you can allow it to exchange energy with its environment. And the aim is to use so there's a microscopic description, so where you have the you know the position coordinates or the momentum coordinates of each of these particles. You also might know the interaction between different particles. Of course, we'll start with an ideal gas where the interaction potential is very simple, and the idea is starting from the microscopics, which is position, momentum, energy, interaction. Can you get out the laws of thermodynamics? Um, so thermodynamics is described in terms of macroscopic variables, which for an ideal gas would be pressure, volume, temperature, and so on and so forth. Uh, if you have a different thermodynamic system, suppose a magnetized material, then the corresponding variables would be the macroscopic variables will be magnetization, right, and an external field by which you could control the magnetization would be the magnetic field. And of course, this magnetic sample can exchange energy with the environment, just like a box of gas can. And depending upon the temperature, its magnetization is going to change. So starting from the microscopic description, can we give a macroscopic description? So how is microscopic relations, interactions, uh, behavior, fluctuations lead to the response or the behavior of some system, a large magnetic system, interacting gas, non-interacting gas, gas of electrons, and so on. So how does its behavior manifest itself in a macroscopic manner, which can be measured in the lab? Okay, so that's what statistical physics is. What is the method? What is the calculation scheme? Right, like for quantum mechanics, you have Schrodinger's equation, and if you have Schrodinger equation, and if you can uh, you can calculate the properties or where a position is or what is the wave function and so on and so forth. Here, similarly, you have large number of interacting particles, and the aim is how do you describe its behavior collectively. So it's an emergent phenomenon. Uh, so that's what the scope of statistical physics is. The books recommended which we'll use is Thermodynamics by Fermi. Somehow it's missing. But two classes, I think, I'll give an overview of thermodynamics, and that will be taken care of by Fermi. And there's a verbose book by Frederick Reif, but it's very good to build intuitions. The problem is this book is extremely spread out. So fundamentals of statistical physics and thermal physics by Frederick Reif is basically whatever I teach, you can go back and check out those chapters or sections and read about it, and you'll basically develop an intuition about it. There's also the book by Kersen Huang, Statistical Physics, and R.K. Patria, Statistical Physics. Now, Kersen Huang starts in the way statistical physics was developed, in which how does a system reach equilibrium, this is Boltzmann work, and later teach how to use statistical physics to calculate the macroscopic property of large number of systems, which is part B. We are going to start with part B, which is basically what Frederick Reif and Patria does. Right, but there will be some topics which we shall take from Kersen Huang because it explains it better. That's the part B of the book. There's also a wonderful book by Statistical Physics of Particles by Mech and Kardar. But that's a very good book, but that's more useful. It's short, it's brief, but it's more useful after you have learned the basics of statistical physics. So basically, I'll be following Patria and Reif. Basically, the topics will be, the order of topics will be Patria. Some of the topics will be taught from Patria. but some of the topics are better taught or better explained in Rife. So we'll follow the topics as explained, as discussed in the order of Wang, part B, or Patria, but the concepts are better here. So there are many ways of teaching statistical physics. And one is the Kersen-Wang approach, which is the historical approach. How did Boltzmann get to the concept of equilibrium? How does a system which is perturbed from equilibrium gradually relax from equilibrium, and then only then after that was the whole statistical physics as we know it was developed. So that's one way to teach it. But what I'm going to do is my approach is a more functional approach. So basically, first get to the idea of, okay, what are the basic postulates, what are the basic ideas, what are the basic calculation schemes, and apply it to a larger class of problems so that you at least develop some intuition of how to use statistical physics. And then go back to the foundations if required, or go back to the foundations in StatMech too. The functional approach has an advantage in that it will one can use statistical mechanics, have some familiarity with calculation tools of statistical mechanics, so that it can be used in other subjects like quantum statistics and atomic and molecular physics and condensed matter one. So that's the approach I'm going to follow. Okay, so with that background, let's go a bit more deeper into what we're going to discuss. Of course, the full details will gradually come. So the origin of statistical mechanics is thermodynamics, and thermodynamics discussed about the conversion of heat into mechanical work and vice versa. And that's a pretty old subject, at least of 200 years. And what statistical physics gives a microscopic basis or a microscopic picture of how thermodynamics originates. Okay, so it cannot fully substitute thermodynamics, because while developing statistical physics, it used the intuitions and results of thermodynamics. So what it did is have a calculational scheme using a set of just two simple assumptions, which is the ergodic hypothesis and the insight that an ensemble average is equal to time average. I know you don't know what is the ensemble average. Well, time average is basically observe a system and measure its properties and see what is its mean values like pressure, say, temperature, say. And so it used these hypotheses, it used these assumptions, and Boltzmann hypothesis that entropy can be written in terms of some Boltzmann constant into log some microscopic quantities. There's a mapping. So this is this hypothesis. He said, please follow this rule, and then you'll be able to calculate entropy as a function of various quantities, and then you will be able to identify. The important word is identify the various things that you calculate thermodynamics wise from this microscopic quantity. You're going to make a one-to-one mapping. You'll say that the properties of this particular quantity has all the properties which we know from thermodynamics. So thermodynamics was there, and why was it there? We'll discuss a bit more. But that's why we're going to discuss thermodynamics for 2 classes and then start statistical physics, because you're going to need to map quantities and behaviors to certain quantities which we gradually developed over 200 years. And the aim of thermodynamics was to basically convert heat to mechanical work. What is mechanical work? Suppose you want to pull out a water from a well, or get a horse to pull stuff from one place to the other. That's work. And the question is, can you design machines which can replace the horse? Right. So there were some rules and laws and concept of heat which was developed, and that in later trying to get more foundational understanding of it, developed statistical physics, and it kept on developing and it's still developing. Okay, so it started with the relaxation of gases to equilibrium. That's what Boltzmann started with, and he could relate some quantity that as it relaxed to equilibrium, there was a certain quantity called the H, which he called the H, and the H theorem, which kept on, I think, decreasing because the negative of H was identified with entropy, and entropy kept increasing. So any reversible process where something started from a certain state and relaxed to an equilibrium, we showed that entropy entropy is always increasing or H is always decreasing. Okay, so that's the connection between thermodynamics and StatMech in a slightly more detail than what I did in the first sentences. Uh, you'll understand this more as we go along. It's a hands-on course again. So thermodynamics deals with properties of a system with macroscopic variables, which are described in terms of microscopic variables using quantities like volume, pressure, temperature, work done, heat transfer, and so on and so forth. So we have a direct connect with it. We can sense these quantities called pressure. We can feel pressure. We can feel uh, not measure, but at least feel higher temperatures and lower temperatures. Of course, it has to be, one needs a thermometer to measure it accurately. One can define the work done force into displacement. So how much force you need to transfer some mass to pull it up against gravity or make it move against friction. So how much work is done. And you need heat transfer, how much energy is given. Statistical physics, on the other hand, is a microscopic description using properties which are beyond our sense perceptions, but using which we can relate macroscopic quantities in terms of microscopic properties. So we'll get out P1, T1, and so on in terms of microscopic quantities like momentum, position, fluctuations of energy, and if you are talking about magnetization, in terms of how many spins or magnetic moments are pointing up and down and how they're fluctuating, and so on and so forth. As I said, we are going to have a quick revision of thermodynamics before we go on. Thermodynamics was developed by experiments and experience of 200 years, and they had already defined different free energies, like there was already concepts of entropy, free energy, Gibbs free energy, Helmholtz free energy, which in turn, depending upon which situation you are, which situation, I mean, if energy exchange is allowed or not, or you sometimes calculate the entropy, you sometimes calculate something called the partition function and relate it to free energy or to entropy. Sorry, so partition function you relate to the free energy, and if you are calculating the total number of microstates by Boltzmann's hypothesis, you see that it has the same properties, suitable log of it has the same properties as that of entropy as defined in thermodynamics. And once you get these, you can take suitable derivatives. Once you have the mapping, you can take suitable derivatives to calculate various thermodynamic quantities. So that's the basic idea. Okay, so thermodynamics. So thermodynamics, the basic idea is to replace horses. work done by horses, force into displacement, work done, and getting replaced by machines. So, right. Uh, so, so this has a pretty long history. It is the first machine, very working machine, however inefficient it might be, was basically designed around 1697. Yeah. So 1697 is a time when Newton is already old, because Newton was born around 1647, I think, and died 1727. The British had already reached India. Aurangzeb was ruling in India, so that's the time. I mean, of course, you can calculate the number of years, but just to give a sense of time. And East India Company was already spreading its wings. 1757, East India Company started, uh, yeah, whatever, taking over the business of ruling India. So we are talking of 50 years before that. So it's 17, sorry, 1698. And somebody savvy built a machine which consumed a huge amount of energy and gave it just 2% of it converted into work. And they still didn't know what heat was. So they thought it was some fluid, and if this fluid goes from one body to the other, its temperature increases. But if they had this concept, there were many inconsistencies, and basically, so 1700s on one hand was uh, try they were trying to improve the efficiency of machines, and sometime making it 15%, trying to convert machines to work done. But they really didn't have much of an idea. So it was more of an engineering approach of somehow getting more work done out. Uh, and towards the later part, they also wanted to know how much, I mean, they knew that they couldn't convert all the heat to work, that they had realized, but how much more efficient they could make it, that they didn't know. And actually, the second law of thermodynamics was proposed by Sadi Carnot in 1824. That's 100 years, 125 years after the first machine was built, converted heat into work, uh, which basically said what is the maximum work that you can uh, obtain in a cyclic manner continuously uh, from a machine from a from a machine working between two temperatures. But even at that time, people didn't know what is exactly heat. And actually, the first law of thermodynamics, which is essentially the statement of the conservation of energy, was developed or was proposed even 30 years after Sadi Carnot proposed the second law of thermodynamics. And the reason it was proposed 30 years later, and the importance of this energy conservation equation, because it was known energy conservation, it was in Newtonian time. The importance is that it gives the idea, the status of heat, which is essentially energy in flow, uh, the same status as work done, a form of energy. Previously, they were thinking that this heat is a form of liquid. They didn't have a concept of uh, the internal energy. So basically, this conservation of energy equation basically says that you can transfer heat and thereby change its internal energy and also get some work done. Right? So this statement, other than the role of saying that the transfer of heat dq will change from one body to the other, it change its internal energy, and also you can get some work done. It also gave the status of dq to be a form of energy in transport, right? And that was not clear at all, uh, right? So that's the reason of the first law of thermodynamics. It's much more beyond the conservation of energy. It was realized that heat is a form of energy. It's a form of energy transfer. And it's through experiments of Joule in 10 years before this first law was proposed that he had shown that work could be completely converted into heat. If you do some work, if you make some roller rotate in water, so the energy that is dissipated can be completely converted into heat, and the energy dissipation that was known, uh, right? But Sadi Carnot had realized that work can be converted fully into heat, but heat cannot be fully converted to work. I mean, in a cyclic manner without any other change in the system. See, finally, what they wanted to do is take a machine, do some work, get it back into its original position, do some more work, and so on and so forth. So you can you can absorb heat, you can get some work done, but if you want to get that system back to its original position without any other change in the system, that's what it means, without any other change in the system, then it is not possible to convert all the heat to work. To get the system back into its original state, if you have know about the Carnot cycle, uh, you have to release some heat. The amount of heat absorbed cannot be fully converted into heat, but to get it back, you have to give out some heat to the system. So some amount of heat is wasted, right? So that's what it means. That's the essence of second law of thermodynamics. And the concept of entropy was actually introduced only in the 1850s by Rudolf Clausius, right? And the term thermodynamics was first used by Lord Kelvin. So he got his lordship and Kelvin name much later. He was called William Thomson. And that was also used sometime around 1854. Uh, it's only after this that the kinetic theory of gases was developed by various people, including Maxwell. Uh, and finally, it's using this Maxwell and Clausius were developing particle physics and statistical physics and kinetic theory of gases. And the Boltzmann's eighth theorem came in the 1870s. And that's the time when he also wrote down S equal to K log omega. Boltzmann's theorem relates to relaxation of a gas to equilibrium using the Boltzmann transport equation, and identification of S with entropy, which was a macroscopic quantity defined in the 1850s, 20 years ago, uh, also came with Boltzmann. Of course, it was not believed. And yeah, so he had to face a lot of flack. And only in the 1890s, the ensemble picture that you will be learning about was developed by the Gibbs. I think this lecture would be more useful after the course was done, but anyway, I have to tell you. So basically, statistical physics is developing starting from 1860s to just the time before quantum mechanics. So Gibbs was working in 1890s, the same time when you already had Michelson-Morley experiment and so on and so forth. So the concepts of canonical ensemble, the grand canonical ensemble, was developed by Gibbs much later. I mean, not much later, 20 years after Boltzmann. And the ideas which were developed by Gibbs was used in 1901 by Planck, and he used StatMech for an ideal gas of photon to get the Planck radiation formula, which you might already have come across. In 1905, that magic here, Einstein also described the equation, uh, statistical equation with fluctuations, and stochastic equation is the right word, to describe Brownian motion. And after 4 5 years, Pera, however you pronounce it, actually did some experiments, and that's how this Avogadro number was discovered. 6.02 into 21 23, right? So, and that also established the particle nature of the liquid. Before that, it was not established. So you understand, it's just 100 years old. So 1926, Bose-Einstein statistics was uh, proposed, discovered, call it whatever English word you want to say. And soon after Fermi-Dirac, we're going to cover all of these in this course, because this is really, as statistical mechanics is developing. And soon after quantum mechanics, large number, you wanted to look at the properties of one electron, one particle in a box, and one particle in an infinite well, and so on and so forth. But thereafter, you also wanted to know about how the hydrogen atom behaves and large number of interacting quantum particles behave, right? And when you look at the conductivity, which is the behavior of a gas of electrons, and that was, I guess, the beginning of condensed matter physics. If you're looking at the statistical properties, the effective macroscopic properties of lattice vibrations, phonons, so that's how condensed matter physics developed. That's why you need to know statistical physics and quantum mechanics, and only after that, in the next semester, is condensed matter physics developed. The concept of heat and temperature gradients, and how it affects transition lines between electrons, right? That's how you figure out distances and how hot various galaxies are, or whatever stars are. So it was soon statistical mechanics was applied to astronomy. So basically, to figure out temperature of the sun, temperature of galaxies, how distant, far something is moving. So quantum mechanics, statistical mechanics, how the lines, the various spectral lines shift at different temperatures. So statistical mechanics, the concept of heat and principles were already being used in astronomy, condensed matter, and atomic and molecular physics, and soon after, new areas of physics also developed, like soft matter, which came much later. So those are much more modern topics compared to, say, astronomy and condensed matter physics, right? Uh, Before thermodynamics came, or in parallel to thermodynamics, what was going on is also gas laws. So they were empirically, experimentally figuring out uh, properties of gases, and of course, the used expansion of gases to convert heat into work. So along with thermodynamics, where the major aim was to convert heat to work and replace horses and pull, and get steam engines, and so on and so forth. Put in coal, you put in wood, and what you get is motion, work done, force, displacement, yeah, work done. And they were using expansion of gases, and they needed to know the properties of gases combined with thermodynamics to design your engine. But also gases are very nice and interesting, especially I saw this concept called the ideal gas, now non-interacting particles, because well, nearly non-interacting particles, because that's where the statistical mechanics, if you have an ideal gas, does it have a particles? Are they colliding? Uh, the development of statistical physics was also helped with the kinetic theory of gases, which was considered much more simple than crystals. And of course, liquid is a much more complicated system than either gases or crystals, right? Because at least there's some repetition. I mean, okay, gas is simple because there's very less interaction. Crystal is a bit more complicated than gases, but at least there's some periodicity. and liquid is more complicated. But just to give you an history, before thermodynamics, so engines were developed, as I told, in 1698, the first one. Newton died in 1927. Before that, there was Boyle, who developed the Boyle's law, and Boyle's law essentially say that if you take a unit amount of matter, I'm intentionally not using the word mole, but suppose you take some amount of gas, and if it's in ideal conditions, it's not very at low temperatures, close to it become a liquid. Room temperature, much of the gases behave such that PV equal to constant. So you apply more pressure, volume will decrease, 1 by V manner. And along came others like Charles. He had proposed in 1780, 100 years, 120 years later, that P by, he had said, I think, V by T. So if you increase temperature, volume is going to increase proportionately if you have a fixed amount of gas. So volume increases proportionately to with the temperature. But it was, though he had figured it out, he had not published it. And it was actually Charles' law was published or whatever, told to people, popularized by Gay-Lussac. So Gay-Lussac around 1810 or 20, so something like that. Yeah, so between 1802 and 1808, he not only gave Charles' law, but attributed it to Charles. Then Gay-Lussac also figured out that if you have a fixed volume, amount of gas and volume of gas, and as you increase temperature, pressure is going to also increase linearly, right? And then at some point, Avogadro came along and he said, okay, I mean, if you take more number of more molecules of gas, keep it at the same pressure and temperature, the volume will increase. So V by N equal to Kb is some fixed constant. Of course, Boltzmann constant came much later. Some constant was proposed by Avogadro, most probably in 1811. The combination of Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law, the combined gas law as PV equal to RT for 1 mole as we know it, was proposed in 1834 by Clapeyron. Okay, and at that point the value of R was not known, and neither was the concept of mole fully developed. So they just said that if you take a fixed amount of gas, then PV by T will have some fixed value. Actually, they were doing experiments with unit mass of different gases. So there was R, this R was, it's different because they were working with unit masses, same mass, and thereby the number of molecules or the fraction of moles of different gases was different. So the combined gas law, as written by Clapeyron, PV by T equal to R, some constant R, was per unit masses, and they had a different value of R for different gases. Also, the way Clapeyron had written it, it was T, in Celsius, the room temperature, plus 267. And only in Clausius in the 1850s, based on the experiments of somebody else, some name with R, did he write down PV equal to, I'm writing Ri because R was different for different gases, T plus 273. It's only in 1873 that Horstman, somebody called Horstman, wrote down that if you write it per unit mole, then you can define something called R, the gas constant, right? And then PV equal to RT for all gases, and R then holds for any gas. Okay? So if you do this, if you write PV per unit mole, and not per unit mass. That was realized as late as 1873, which is basically, I think, 150 years before that. And yeah, so that was fully British India. So this concept, so I actually while preparing for this class, I was wondering, where does this concept of R come in? When was it developed, and so on? So this story that I told you here is taken from an article called "The Universal Gas Constant R" uh, by William B. Jensen, California State University. You can find it out, the history of gas constant. And the other things that I've been telling you is basically references from the history of thermodynamics Wikipedia page, brief history of thermodynamics as illustrated by Books and People, Gregory Girolami, published as recently as 2020. What he has done, and was an online article. Previously, all these pictures were there in the books in the library, but now he has taken pictures from there, scanned it, and made it an article so that it's easily accessible to you guys. And some of these ideas are also taken from the history of thermodynamics. I was just wondering, how did StatMech develop and how was thermodynamics developed? So I just looked back into history. It's The Missing Manual by Wayne M. Saslow, 2022. And of course, I already told about this. So here are some pictures. This is the picture of Sadi Carnot, the guy Clapeyron, who wrote down PV equal to nRT, or some version of it, not the version that we know of today. Clausius, who actually figured out 273 degrees centigrade, and he had many other contributions. You might have heard his name in thermodynamics course. I haven't put a picture of Boltzmann, Ludwig Boltzmann, because statistical physics essentially is Boltzmann, but his pictures are and stories are often available. Rather, I have put a picture of Gibbs, who gave the ensemble picture of statistical mechanics. Okay, so with that, I shall end today's class, and we start from a quick revision of thermodynamics. And before that, why do we need statistical physics? What is the current status of statistical physics? 2-3 minutes, I'll give some discussion. And we'll start next class. Okay, so with that, I shall stop share, and also how do I post caption? Don't tell me I didn't record it. Oh, where is recording?